Hey guys, how's it going? And welcome to another tutorial on Quantum Espresso. Now, I've seen a lot of people asking me about how to get the value of the band gap for the system by running only an SCF calculation. So the thing is that they know that how to get the band value by calculating the band structure or the density of states, and then they can find out the band gap from those. However, what they want to know is if it is possible to do it by only running an SCF calculation, and the answer is that it is very much possible, and there is not a lot of changes that you need to make in your calculation. So the first thing is that occupations. So usually for insulators, what you should have is you should have your occupations to be fixed and not to set to smearing. So if you have your occupation set to smearing, then the Quantum Espresso prints out the Fermi level for in the output file. However, if you change it to fixed, then it will print out the value of the highest occupied level. So what Quantum Espresso will do now is it will calculate the energy for the highest occupied level and all the occupied states, and will print out that value instead of the Fermi level. But what you are interested in is you also want the band gap, that is, you want the information about the lowest unoccupied level also. So in order to get that, you will have to tell Quantum Espresso to calculate energies for more states than only the occupied states. So you will have to provide another parameter called NBNG, that is basically it is specifying the number of bands. Now, since we are working with a silicon crystal, so you can set it to 32 to get the all the energies for the unoccupied as well as the occupied states. However, even if you just set it to a few more than the number of occupied states, so let's say if your occupied states are like 16, so you can even set it to 18 also to get the band gap. But for the sake of this tutorial, let me just set it to 32, and we will run this calculation now. So just go ahead and run this calculation with these two changes, that is set your occupations to be fixed and the number of bands to be 32 or anything greater than the number of occupied states, and then you will in the output file you will see the value of the band gap. So just wait for the calculation to complete. Okay, so the SCF has converged, and now we can have a look at the the band gap. So what you are looking for is you are looking for this line, that is the highest occupied state and the lowest unoccupied level. So if you can find it, then you can just search for it by like this. So here you have the values. So as you can see that the highest occupied level is 6.6, while the lowest unoccupied level is 6.6, while the highest occupied level is 5.9. So that corresponds to a band gap of like 0.6 something. So you can see that the DFT is underestimating the silicon band gap by a significant bit, that is the original band gap is 1.1 electron volts or something. So that is how you get the band gap value. And in contrast to this, if you don't provide this n band parameter right here, so let me just quickly run one more calculation without this parameter, and just wait for the calculation to complete. Okay, so the SCF has converged, and if now you search for this line, that is highest occupied level, then you will see that Quantum Espresso has only calculated the highest occupied level, and it has not calculated the energies for the unoccupied levels, because we did not force Quantum Espresso to do so. So that's why you needed to provide the n-band parameter. However, you don't need to provide like 32 bands. You can probably get that value with a lot less. And then finally, you should also remember one thing, that occupations should be fixed for an insulator or anything with a band gap, and it should be set to smearing for metals. Well, that's all. And in case you guys learned something from this video, enjoyed it, then don't forget to hit the like button and subscribe to my channel for more videos like this. Thanks for watching, and have a great day.